Okay, so this is a review session for Math383 complex analysis. And so the question was on the Fresnel integral. And however I'm pronouncing it is almost surely not the correct way to pronounce it. And so we have the following situation. Something like this. And then the contour we're going to have, we come along the x-axis, come up to 45 degrees, not drawn to scale, and then come down like this, where this is pi over 4. And they want us to integrate the following function. So f of z is e to the negative z squared, and then the angle is pi over 4. And we're given the following. I need to give us the integral from minus infinity to infinity, but that's the same as from 0 to infinity, because things such as that the integral from 0 to infinity of e to the negative x squared dx is the square root of pi. Or is there two? Or is it?
I think it's over 2.
Over 2?
Like from both sides.
Yep, something like this. Okay. And again, this is the Gaussian integral. This is one of the most important integrals in all probability. It can be done using standard real analysis techniques. The best way to do this is actually to square the integral and change variables to polar. So we will assume that we know this. And the goal is to calculate integrals of cosine of x squared, sine of x squared. And we're doing these from 0 to infinity, right? And, okay. So there's 3 pieces. The piece on the x-axis we know, the book tells us. We want to calculate the piece on the 45-degree line and the piece on the arc. And in a completely surprising choice of notation, we'll call the arcs or the segments gamma 1, gamma 2, gamma 3. The only chance you typically have for problems like this is if the integral of a gamma 2 goes to 0. And so let's think about what's going on. So, whoops. So we have z squared is x squared minus y squared is the real part, plus 2i xy is the imaginary part. So e to the negative z squared is going to be e to the y squared minus x squared, e to the negative 2i xy. So when we look at this, some things make us happy, some things make us concerned. The e to the negative 2i xy, that's going to have absolute value 1. That's not going to really contribute to any growth along the arc. The e to the negative x squared is great. The larger x is the smaller that's going to be. The problem is the e to the y squared. And y could be quite large. But the good news is y can't be larger than x. Right? Because the intersection is at the 45-degree point. And so we know the worst case scenario is y equals x. And at that point, then it's of size 1. The problem is, we will say that this has length r. So the length of the arc is going to be what? Exactly. I believe it's pi fourths r. Because if we had the whole thing 2 pi, it would be 2 pi r. We have pi fourths. And this is why we use radians, because there's a nice correspondence. So unfortunately, the arc has a sizable length. And because the arc has a sizable length, if we try to replace the function with its largest value, it's deadly. So the solution is to break the arc into different segments and to try to attack it using different bounds in different places. So here is the 45-degree line. And then what I'm going to do, again, I'm not going to bother trying to draw things to scale. Here's my arc. And what I'm going to do, oops, I somehow went to erase, is you're again not drawn to scale. I'm going to break the arc into 2 parts. So the big angle is pi over 4. The smaller angle, let's call it pi over 4. Now we have to subtract something. So there's a lot of different ways we can do this. One is the method of divine inspiration, where you know what the answer is. Let's do it without using the method of divine inspiration. We're going to have to subtract something. Do you think that something should depend on anything at play in this problem?
Probably depend on.
It should depend on r. So let's subtract off some function of r. Let's call it g of r. So if we think about this, we can then talk about what is the length of this arc over here. That's just going to be r times g of r. And again, what I really care about is the thought process. So if this is r times g of r, we need the contribution of this piece to be going to 0. Unless we want to do a tremendous amount of work and take into account how y is changing and x is changing on this integral, if we want to just be crude, we would approximate the function by its largest value, which is 1. Now, we can do a little bit better, because as we go down, the function, the argument is going to change a little bit. But the, whoa, somehow I zoomed in. So the contribution from the small arc is at most going to be the arc length times the maximum value, an absolute value. And that's going to be less than equal to r g of r times 1. So therefore, g of r needs to be small enough so that we need r g of r to go to 0. We need r g of r to go to 0. Could try g of r equals 1 over r log r. Or we could try g of r is r to the 1 minus eta. I'm sorry. To the you write it this way, as to 1 over r to the 1 plus eta. Any of those would work. Those are the two natural choices. Which do you think is a better choice? 1 over r log r or 1 over r to the 1 plus eta? So logs are hard. So the power is nice. So again, this is a chance for me to philosophize a little bit. We're not under the 50-minute pressure. When you prove Riemann sums converge to the area under the curve, you don't really care about what's going on at a finite partition. You only care about in the limit, as things go to infinity, the upper sums and the lower sums converge, and they converge to a common value. So I don't really care about how this is happening. Now, if I have to numerically calculate something, then I care. And then I care about what the error terms are. But in this, if we're taking r to the limit, it doesn't really matter what's going on at any finite cut, because I'm taking the limit as r goes to infinity. So which would you rather have, 1 over r log r or 1 over r to the 1 plus eta? One of them is actually much better than the other. Yeah, so which one do you think will allow you to utilize limiting behavior more easily? I've lost the screen. Okay, natural. Okay, so which one do you think is going to work better? So the cable is loose, but fortunately there's two different ways of moving. Let me try connecting the other way. To be better. The 1 over r log r or the 1 over r to the 1 plus eta? They both work on the small arc. Which would you rather have on the large arc? Which has a bigger small arc? The 1 over r log r or the 1 over r to the 1 plus eta? So which gives a bigger small arc? I'm sorry? Eta is some parameter. So eta is some small positive number.
Any power is going to end up growing quicker than log.
Good. So any power is going to grow faster than logarithm. So which is going to give you a larger arc? The 1 over r log r or the 1 over r to the 1 plus eta?
Probably the one with the log will like get smaller, slower.
Yes.
So you don't want that one.
No, you want that one. You want that one. If you think about it, both of them work for showing that the contribution in the small arc is fine. I would much rather have whichever one of these gives me a larger arc, because then that gives me a smaller maximum value of y. Because when you think about the next part, we then have to show that on what's we'll call like the green segment, we want to understand what's the contribution here. And so we care about what's the largest value of y. We're going to have an e to the minus x squared. So the smaller value of y we get, the better shape we're in. So I would much rather use the 1 over r log r. I think both will work, but my gut feeling is the 1 over r log r is better because that gives a larger arc. And since we can already handle things there, I would like to take the largest thing possible. What if we needed something that was a little bit larger than 1 over r log r? What could we do? So I still need rg of r to go to 0, but I want it to go to 0 even slower than 1 over r log r. Yeah, you could do 1 over log log r, or log log log. You know, you could keep playing games like that, so that you just barely, and that makes the arc, you know, bigger and bigger and bigger. But you know, the hope is that it's not going to be so delicate that this will matter. Okay, so now let's move on to the next part. So now we want to figure out how to handle the remaining piece. And so we have, you know, the part of the arc over here, and then we have, you know, from here, you know, downward. And so now, so this is the angle pi/4 minus g of r. We want to figure out what is the corresponding value here. We'll call this y sub r. And we know that the absolute value of f of z is going to be equal to e to the negative, e to the y squared minus x squared. And we agree that the worst case is going to be at that critical value y sub r for this segment. So the contribution is at most, you know, arc length times the absolute value of the maximum value, which is going to be less than equal to, what's the arc length?
R times pi/4 minus 2r.
Yes. But I can just write it as r times pi/4, because the fact that I'm subtracting a little bit, I'm not going to win by that. You know, it's not even going to be enough to change multiplicatively what the coefficient is. And then the maximum value would be e to the negative, let's call it e to the y sub r squared minus xr squared. Now we know xr squared is greater than yr squared. Because we're past the 45-degree line. So the hope is we've moved far enough down that we're okay. So I'm going to just go to a new page to just start writing this because the trig is going to be a little bit involved, but yeah, there's a couple of ways to do this. We could factor this as how much trig do you remember? So xr is going to be r times cosine of pi-4 minus 3. So there are identities for the sum and the difference of cosines. And so one possibility is I could factor the yr squared minus xr squared as yr minus xr times yr plus xr, use the identities, and go through that way. Do yr squared minus xr squared is yr minus xr, yr plus xr. Now, one of the things that's nice about that is yr plus xr is not going to be too bad. Again, if you don't mind, I think it's nice to talk about multiple ways to do this problem because we don't really care about this problem at the end of the day. We care about how do we attack problems in general. And looking at a difference of squares, this would now be, the absolute value of, yr minus xr. We've got to be careful because this is negative. So, we want to say that this is, something like a little bit great. Let's see if it gets a little bit annoying. No. So this would be yr minus xr. You would get, r cosine pi-4 minus g of r minus sine of pi-4 minus g of r. And cosine is going to be larger than sine here. And then you would have the sum. Cosine pi-4 minus g of r plus the sine of pi-4 minus g of r. Now, what is the cosine of pi-4 minus g of r? What is that approximately? Yeah. Right. So the second piece is approximately root 2 over 2 plus root 2 over 2. It's approximately root 2. So if we made that a little bit smaller than root 2, we would make this whole thing a little bit less negative. And so we could use that if we wanted to try to do a bounding, that we know this is going to be very close. So we know that this piece here is approximately root 2. Oh, and I'm sorry, I dropped, this should be an r in each of these terms. So I'm going to pull out that r, that's going to give me an r squared. So really, we want to just look at cosine minus sine. And so if we focus just on this part, that's going to be cosine of pi-4 cosine g of r. Now, because it's a minus, that means it's going to be a plus sine of pi-4 sine of g of r. And now we have to subtract the sine. So then we would subtract, it's going to be the sine of pi-4 cosine of g of r. And now because it's a minus, it's a minus, but a minus of a minus is a plus. And then we'll have cosine of pi fourths sine g of r. Because the sine of a minus b is the sine of a cosine b minus the cosine of a sine of b. But since I'm subtracting everything, the signs get switched. Well, what's nice is you can see the second terms reinforce, because the cosine of pi fourths is the same as sine of pi fourths, and the first two terms cancel. So this whole thing just becomes root 2 over 2, root 2 over 2 becomes just root 2 sine g of r, which is approximately root 2 times g of r. The next term is going to be much smaller because g of r is very small. So the next one will be minus, g of r cubed over 3 factorial plus dot, 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 dot. So now, putting all the pieces together, we would get e to the y r squared minus x r squared is going to be less than or equal to e to the, let's think about it. If I have something that's negative, so if I take the second piece, which was root 2, approximately, and I replace it with 1, it's not quite as negative as it used to be. So I've made it larger. And so I would have, root 2 oh, wait a minute. Okay. What I wrote up over here is, I apologize. I wrote xr minus yr. This is xr minus yr. We have yr minus xr. That's where the minus sign is coming from. So it's going to be minus root 2 g of r. And if I include the next piece, I'm going to make things a little bit larger. So that would be plus, and I'll drop the 3 factorial to make it a little bit larger, plus, root 2 g of r cubed. And this should all be multiplied by r squared. Well, g of r is going to be at least 1 over r. So when we have r squared divided by that, the g of r cubed term doesn't really matter. So, again, I hope you can see with a little bit of algebra, this is at most, 2023 e to the negative root 2 r squared g of r. Does that seem reasonable? And again, what I'm doing is I'm not going for the best possible bound. I'm always taking just, let's argue as crudely as possible, see if this works. There's really no point in expanding this carefully if I have so much decay that I'm already winning. And so now let's look at the contribution. Now we have, we want to integrate over the green arc. And so, to integrate over the green arc from here to here, that's going to be the integral. Well, let's bound it by the green arc. It's going to be less than or equal to e to the negative root 2 r squared g of r, 2023, which is at most pi fourths times r. Right? So this is less than or equal to some constant. And then we're going to have r in the numerator. Then we'll have an e to the root 2 r squared g of r. Oh, okay. we've got plenty of decay. We could actually afford to take g of r to be 1 over r to the 1 plus eta. If eta is close to 1, we're in trouble. But if eta is small, we could actually do a power savings. We could have an extremely small arc there. The smaller g of r is, then the smaller the exponent is going to be, the smaller the denominator is going to be, the more trouble we have. The larger g of r is, the easier things are. So here, typically you have competing influences. And in a lot of problems, what you sometimes do is you might say, let me choose g of r to equalize the contribution of the two pieces. But here, I just want both pieces to go to 0. And so, if g of r equals 1 over r log r, or 1 over r to the 1 plus eta, with eta less than 1, we win. And then we're just going to have an r over an e to an r. How would you prove that the denominator beats the numerator? So how would we prove the denominator beats the numerator?
Something that
So you just have to prove to me that the denominator goes faster than the numerator.
I mean, a growing exponential is going to be later.
Okay, so prove it. How would you prove it? So I mean, if you say one word, it has a hyphen and some accent marks, that would suffice. L'hôpital. So you could do l'hôpital. Right? Another thing you could do is, e to the u is less than equal to 1 plus u plus ... So we have something that's going to be less than equal to r over root 2 r squared g of r, which clearly goes to 0. Or if that's not enough, we could do plus u squared, and we could multiply this by 2 over 2, something like that. So with the exponential, just take one term of it, and that's enough. So even if we did, g of r was, say, eta is 1/2. Well, now all of a sudden we have r to the 3/2, dividing r squared. That's only r to the 1/2. That's not enough. But if we go far enough, but you can see now why 1 over log works nicely. So you can either use l'hôpital or you can use this. This now shows that we don't have to worry about that arc. So all we have to do now is just deal with the integral along this line, where this has length r, and this angle is pi/4. Are you comfortable doing that, or should we keep? Sure, we can do it. The other thing that's worth remarking is over here, we factored. We didn't have to factor. We could have just calculated xr and expand the cosine as we did below. We could have calculated yr, expand as before, and then subtract. If you do that, a lot of things are going to cancel. It might be a little bit cleaner in terms of just how you want to do the algebra. It's probably not a bad idea to just try to do that. Knowing that it factors is a nice way to handle the algebra. But it's not the only way. You could just expand both of them, and then you'll notice a lot of things cancel. And you can see now why the 45 degrees is so essential for this problem. Everything is perfectly aligned. And that's one of the real challenges when you're doing a subject like this, is if you happen to choose the right contour, then you can do miracles. All right, so now let's look at what's going on over here. So now let's write z as r e to the I theta. Theta Sorry. No, I don't want to. I don't want to do it like that. Yeah, we'll do it like that. So theta for this problem is going to be fixed. It's always going to be pi over 4. And this should actually not be an r. I should really call this x. And x is going to go from r down to 0. That's going to parameterize the line that I'm coming down. So then dz would be e to the I theta dx. E to the negative z squared. All right. That's going to be e to the negative x squared e to the 2I pi over 4. Guess I go to use pi over 4. That's going to be root 2 over 2 plus I 2 over 2. Well, what is e to the 2I pi over 4? Okay, what's e to the?
That's going to end up being I.
And that's just going to be I. So this is going to be e to the minus I x squared, which is cosine x squared, I think minus I sine x squared. So now we have the integral x goes from r to 0. I like to just write things very carefully. Cosine of x squared minus I sine of x squared. And then we're going to have, I'm going to just pull out the root 2 over 2. And then we'll have 1 plus I dx. Now, when we add that to the first piece, which was going to be root pi over 2 in the limit, and add it to the last piece, which is 0 in the limit, right? We get the integral over the closed contour. And what's the integral over the closed contour? It's got to be 0, because we don't have any poles. So we know that the integral of cosine x squared minus I sine x squared times 1 plus I dx plus pi halves is 0. Now, what's interesting is, we can expand things out a little bit. So we have root 2 over 2 integral from, I'm going to switch the order of integrals, which gives me a negative sign. So I'm going to bring it over to the other side so the negative sign is gone. Now x goes from 0 to r of cosine x squared minus I sine x squared 1 plus I dx equals root pi over 2. I can cancel the 2's. Now, if you think about this, I can divide by the root 2 if I want. And so I'll put the 1 over root 2 over here. So now, let's look at the real and the imaginary parts. We have the integral from 0 to r of cosine x squared plus sine x squared dx. That's the real part. And then the imaginary part, we're going to have the integral from 0 to r. And so we're going to have I hitting cosine x squared, right? And then we're going to have 1 hitting the minus I sine, so it's going to be minus sine of x squared dx equals root pi over root 2. So we really have two things we don't know. Let's let A be the integral from 0 to r. I guess we should really be doing 0 to infinity at this point, but rather than erasing anything, I'll just set I equals infinity. So we'll have, at least from this point onward, I'll start writing infinity. So we'll have A be the integral from 0 to infinity of cosine of x squared dx, and B will be the integral from 0 to infinity of sine of x squared dx. And now here's where the miracle is. We get A plus B equals square root of pi halves. And the other one is I times A minus B equals 0. This is a very easy system of equations to solve. The second one just tells us A equals B. And then using that, we then get A equals B equals root pi halves over 2. So hopefully I haven't done any of the algebra wrong, and that this is the answer the book claims.
Root 2 is root 2 pi over 4, right? Does that say what their individuals is?
This would be equal to the square root of 2 pi over 4. Because I multiply by root 2 over root 2.
Yeah, they want root 2 pi over 4.
Right. And so Serge Lang and Yale said if the Greeks had been very intelligent, they would not have invented pi, they would have invented 2 pi. And you can argue which is the true fundamental constant. But if you look at this, the integral of cosine x squared and sine x squared, initially it's not clear that this should converge. Right? But what happens is there's so much oscillation in what's going on that the period, if you remember your trig, the period of cosine bx is 2 pi over b. So the larger the coefficient is, the shorter the period is. And so here, if you view x squared as x times x, the period is getting smaller and smaller and smaller and smaller. So it's oscillating faster and faster and faster and faster. And so it's essentially canceling itself out. And so when you think about how much can it gain versus then how much does it immediately drop off, you're going to have these alternating series of plus minus plus minus. And so, if you try to integrate the absolute value of this, it would be a nightmare. It would not be doable. But the oscillatory one like this, it's going to have a region of length where it's positive, and then it will have a smaller region where it's negative. Then it'll have a region that's even smaller where it's positive. And so you can see that there is hope that at the end of the day, you should get something that's integrable. So this is a really good problem. There's a lot of wonderful techniques in this. It turns out that these integrals have applications in physics. You've done some physics? Small amount. You have to go a little bit deeper. I think they show up in some optics problems. Now, just because we have a few minutes left, have you ever seen a proof, that the integral from minus infinity to infinity of e to the negative, x squared over 2 dx equals the square root of pi, or something like that?
I think so, but I would not mind seeing it again.
This is something that's worth seeing. Actually, I think this should be the square root of 2 pi. And so here's the proof. So let's let I for integral be the integral from minus infinity to infinity of e to the negative x squared over 2 dx. So I squared is the integral x goes from minus infinity to infinity, e to the negative x squared over 2 dx, integral y goes from minus infinity to infinity, e to the minus y squared over 2 dy, which is the integral negative infinity to infinity, negative infinity to infinity, e to the negative x squared plus y squared over 2 dx dy. So we're integrating over the entire plane. We've got a function that only depends on x squared plus y squared. What should you be thinking? circle is polar. So r squared is x squared plus y squared. Dx dy is dr times r d theta, which we always write as r dr d theta. But you should really view it as infinitesimal dr, which is a length, and then r times infinitesimal theta. And so now our integral is going to just be the same as the integral r goes from 0 to infinity, integral theta goes from 0 to 2 pi, e to the negative r squared over 2 r dr d theta. The theta integral is easy, just gets your 2 pi. Integral r goes from 0 to infinity, e to the minus r squared over 2 r dr. You know, boy, we live life well. When you take the derivative of e to the negative r squared over 2, you just get negative r. And so everything is nice. This is one of the reasons why it's nice to have the 2 over there. So this is then going to just become 2 pi, and you're going to have e to the negative r squared over 2. And then because of the negative sign, we have to switch the boundary. So it's infinity and 0 flipped like this. Well, when we put in e to the negative infinity, that's just going to be 0. When we put in 0, we get 1. So we just get 2 pi. So I is equal to the square root of 2 pi, as I is clearly greater than 0. And that's, you know, one way to get the normalization constant for the Gaussian. And this just, you know, completes the problem if you've never seen this before. They often do this in multivariable calculus. I remember seeing this as a freshman in multivariable calculus and just being absolutely amazed. This is a wonderful example of sometimes it's better to take one step backwards to take 2 steps forward. The best way we know to do this integral in one variable is to convert it to a 2-variable integral and then do a change of variable, because we have more powerful techniques available in multivariable calculus. So this is an outstanding problem. There's, you know, so much good stuff going through it. The most interesting part is just be able to look at something like this and say, okay, I want to go down some bit so that in the first arc, I don't care that the function is large of order 1. I'm going to have the arc length is so small that it's not going to matter. Now, the problem is the arc length is going to infinity. So to be really small, that's quite meaningful. And then the question is always, could we have done a better job? Well, over here, we do have an e to the negative x squared. So if we allowed ourselves to exploit some of that, could we do a little bit better? Well, the problem is this arc length is so large that if we move just a little bit in terms of the angle, that's going to be a sizable amount. And so it might be hard to exploit the cancellation coming from e to the negative x squared. We could try to take that into account, because as x gets very large, we're in great shape. You know, another thing you could do is you could put another slice and you could throw away a lot of the arc near x equals r. Because near x equals r, x is going to dominate the y piece. And then, you know, try to figure out what can we say in that region? Can we somehow exploit? You might be able to do something like that, which would allow you to take maybe a larger or a smaller arc in the beginning. But a lot of times there's no need. There may be a need, however, for a future problem. And that's why it's a good idea, it's a good habit to learn how to do these problems in some generality. Is I'm not trying to just immediately write down, you know, the answer is, let's take 1 over r log r. Let's have some free parameter. And, you know, one way to do it is 1 over r to the 1 plus eta, where eta is free. And then I see what eta do I need. Another way is to say, I'm just going to call it g of r and see what kind of conditions do I need on g of r for things to work. And one of the things you quickly realize is it's got to be such that, you know, r times g of r goes to 0. And that's all we need for the first part. For the second part, we had a little bit that we... So we just needed, you know, r divided by e to the r squared g of r. it's going to be really hard for R squared G of R. You know, we're not going to have G of R of size 1 over R squared. Now, if we did do that, that would give us a really short arc, and then we'd be fine. But if G of R was as large as 1 over R squared, we'd be in trouble. If G of R was of size log R over R squared, ooh, now it's really close. And now it's going to come down to what the constants are, because we'd get R to a power. So if you did G of R is log of R over R squared, you could probably make that work if you put in the right constant, if you really wanted a small arc there. But again, it's trying to see how far can we go before we get into trouble. Okay,